Electrons are charged particles that move through electrical circuits, similar to how cars are vehicles that move through traffic networks. Feeders are large electrical lines that carry electricity from power plants to distribution centers, analogous to freeways, which are large roads that carry traffic from one city to another. Branch circuits are smaller electrical lines that connect individual devices to feeders, much like surface streets are smaller roads that connect residential areas to freeways. Overloads occur when too much electricity is flowing through a circuit, causing it to overheat. This is similar to traffic jams, which happen when too many cars are trying to use a roadway, causing it to slow down. A single-pole switch is an electrical device that allows current to flow in only one direction, resembling a stop sign, a traffic sign that requires vehicles to come to a complete stop before proceeding. A dimmer switch is an electrical device that controls the brightness of a light, comparable to a yield sign, a traffic sign that requires vehicles to slow down and yield to oncoming traffic. A short circuit occurs when two wires with opposite charges touch each other, causing a sudden surge of electricity. This is analogous to a head-on collision, where two cars moving in opposite directions collide. A ground fault occurs when electricity flows from a circuit to the ground, similar to a car slamming into a guardrail, as the electricity flows from the car to the ground. Overcurrent protection is a device that protects electrical circuits from overloads and short circuits, just like the highway patrol is responsible for enforcing traffic laws and preventing accidents. In essence, the flow of electrons in an electrical circuit can be understood through the analogy of automobile traffic flow. Considering the nature of electrons, it's crucial to remember that electrons are subatomic particles with a negative electric charge. Their movement constitutes electric current. This movement isn't random, but rather directed by an electric field. Now let's delve deeper into the components of an electrical circuit and their traffic equivalents. Feeders, the electrical highways, are designed to carry large amounts of current from the source to various distribution points. These are typically high-voltage lines to minimize losses over long distances. Just as freeways efficiently move large volumes of traffic, feeders efficiently transport electrical energy. Branch circuits, on the other hand, are the local streets of the electrical system. They distribute power from the feeders to individual loads such as lights, appliances, and outlets. The current carrying capacity of branch circuits is lower than that of feeders, reflecting the lower traffic volume on surface streets. Overloads, the traffic jams of the electrical world, occur when a circuit is carrying more current than it's designed to handle. This can happen when too many devices are plugged into a single circuit, drawing excessive current. The wires heat up due to the increased current flow, potentially leading to insulation damage and fire hazards. Similarly, traffic jams occur when the number of vehicles exceeds the road's capacity, leading to congestion and delays. Protective devices such as circuit breakers and fuses are like the highway patrol of the electrical system. They are designed to interrupt the circuit when an overload or short circuit occurs, preventing damage to the system and ensuring safety. Circuit breakers can be reset, while fuses must be replaced after they blow. A single pole switch controls the flow of current in a single circuit, acting like a stop sign in the electrical world. It can either open the circuit, stopping the flow of current, or close the circuit, allowing current to flow. Dimmer switches, on the other hand, allow for variable control of current flow, similar to a yield sign, where vehicles are allowed to proceed, but at a reduced speed and with caution. They use various techniques, such as resistors or electronic components, to reduce the voltage applied to the load, thereby dimming the light. Short circuits are dangerous situations that occur when there is an unintended low-resistance path for current to flow, analogous to a head-on collision. This results in a very high current flow, which can quickly overheat wires and cause fires. Short circuits are often caused by damaged insulation or faulty wiring. Ground faults occur when current flows from a live conductor to ground, which is typically the metal enclosure of an appliance or electrical equipment. This can happen due to damaged insulation or loose wiring. Ground fault circuit interrupters, or ground fault circuit interrupters, are designed to detect ground faults and quickly interrupt the circuit, preventing electrical shock. Overcurrent protection, like the highway patrol, is crucial for electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect circuits from overloads and short circuits. They are sized to match the current carrying capacity of the circuit and will trip or blow when the current exceeds that level. The National Electrical Code, or NEC, provides guidelines for the proper selection and installation of overcurrent protection devices. For example, NEC Table 310.15b16, formerly 310.16, specifies the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees C through 90 degrees C, in free air, based on conductor size and insulation type. Understanding these analogies can help you visualize the behavior of electricity and appreciate the importance of electrical safety. Just as traffic laws and safety measures are essential for preventing accidents on the road, proper wiring practices and the use of safety devices are crucial for preventing electrical hazards. In the same way that a driver needs to understand the rules of the road, it is very important to know how electricity works. It is also important to use safe measures and practices. Imagine electrons flowing through a wire like cars on a highway. The voltage is like the pressure pushing the cars, and the current is like the number of cars passing a certain point per unit of time. The resistance is like the friction slowing the cars down. Now, let's consider a few more detailed examples. Suppose you have a 120 volts branch circuit protected by a 20 amp circuit breaker. This means that the circuit is designed to safely carry up to 20 amps of current. If you plug in too many appliances and the total current draw exceeds 20 amps, the circuit breaker will trip, interrupting the circuit and preventing an overload. This is like a traffic jam on a highway, where the number of cars exceeds the road's capacity, causing congestion and delays. The circuit breaker acts like a traffic control system, preventing this situation from getting out of hand. Next, let's consider a short circuit. Imagine two wires with opposite charges accidentally touching each other. This creates a very low resistance path for current to flow, resulting in a very high current flow. This is like a head-on collision between two cars, where there is a sudden and violent release of energy. The high current flow can quickly overheat the wires and cause a fire. The circuit breaker or fuse will quickly interrupt the circuit, but not before some damage has occurred. Finally, let's consider a ground fault. Imagine a damaged wire accidentally coming into contact with the metal enclosure of an appliance. This creates a path for current to flow to ground, which can be dangerous if someone touches the appliance. A ground fault circuit interrupter is designed to detect this situation and quickly interrupt the circuit, preventing electrical shock. The ground fault circuit interrupter acts like a safety net, protecting people from harm. In conclusion, the analogy between electron movement and automobile traffic can be a helpful tool for understanding basic electrical concepts. By visualizing electrons as cars, voltage as pressure, current as traffic flow, and resistance as friction, you can gain a better understanding of how electrical circuits work. And by understanding these concepts, you can appreciate the importance of electrical safety and take steps to prevent electrical hazards. Understanding the role of overcurrent protection is key to a safe electrical system. Just like a highway patrol monitors and manages traffic flow to prevent accidents and congestion, overcurrent protection devices safeguard electrical circuits from dangerous conditions. These devices are designed to interrupt the flow of current when it exceeds safe limits, preventing damage to equipment, minimizing the risk of fire, and protecting individuals from electrical shock. The operation of overcurrent protection devices relies on the principles of heat generation and electromagnetism. When current flows through a conductor, it generates heat. The amount of heat generated is proportional to the square of the current. In a circuit breaker, this heat causes a bimetallic strip to bend. When the current exceeds the breaker's rating, the bimetallic strip bends enough to trip the breaker, interrupting the circuit. Fuses, on the other hand, contain a thin strip of metal that melts when the current exceeds the fuse's rating, opening the circuit. Both circuit breakers and fuses are designed to respond quickly to overcurrent conditions, minimizing the duration of the fault and the potential for damage. The selection of the appropriate overcurrent protection device is crucial for ensuring the safety and reliability of an electrical system. The device must be sized to match the current carrying capacity of the circuit it is protecting. If the device is too small, it will trip or blow unnecessarily, disrupting service. If the device is too large, it will not provide adequate protection in the event of an overcurrent condition. The National Electrical Code provides detailed guidelines for the selection and installation of overcurrent protection devices, including tables that specify the allowable ampacities of conductors and the appropriate size of circuit breakers and fuses. In addition to circuit breakers and fuses, other types of overcurrent protection devices are available, such as ground fault circuit interrupters and arc fault circuit interrupters. Ground fault circuit interrupters are designed to detect ground faults, which occur when current flows from a live conductor to ground. Arc fault circuit interrupters are designed to detect arc faults, which are dangerous electrical discharges that can cause fires. These devices provide additional layers of protection against electrical hazards. Regular inspection and maintenance of overcurrent protection devices are essential for ensuring their proper operation. Circuit breakers should be tested periodically to verify that they trip at the correct current level. Fuses should be replaced immediately after they blow. Ground fault circuit interrupters and arc fault circuit interrupters should be tested monthly to ensure that they are functioning properly. By understanding the principles of overcurrent protection and following the guidelines of the National Electrical Code, you can create a safe and reliable electrical system that protects people and property from electrical hazards. Remember, electricity can be dangerous if not handled properly. Always consult with a qualified electrician if you have any questions or concerns about electrical safety. Also, in a commercial building, knowing the voltage is also important to know. For example, knowing the difference between 208 volts, 277 volts, and 480 volts is important. Understanding three-phase power is also equally important, including how to properly measure the voltage and amperage.